Bismillahirrahmanirrahim. In this video we will discuss the state space representation of a differential equation with derivatives of the forcing function. In the previous video we have seen the state space representation of a differential equation without the derivatives of the forcing function. So here you can see the differential equation a naught into y triple dot plus a1 into y double dot plus a2 into y dot plus a3 into y, and that is equal to b naught into u triple dot. That's the third derivative of your input or the forcing function. U double dot, that is the second derivative of your forcing function. U dot, first derivative of your forcing function. So it's a third order differential equation which includes the derivative of the forcing function. So let's represent it with equation A. Now if I rearrange this equation, I can write it like that, the third derivative of our output, that is y, is equal to minus a1 into y dot. So this term will be shifted to this side. Similarly this one over here and this one over here. So shifting all these terms to the right hand side, we will get this one, and these are the terms from here, right? So we can write down this equation A like this. So let us call that this is equation B. Now the first step is to define the state variables. So we will define state variables in such a way that the derivative terms of the forcing function become 0. Okay, let's assume that our first state variable is x1, that is equal to y minus beta naught into u, where this beta naught is the constant, and this constant later on will be described in such a way that the derivative terms of your forcing functions becomes 0. So all these terms will be made 0 by selecting a suitable value of this constant beta naught. Okay, so the first state variable is x1. The second state variable, that is x2, is defined as x1 dot minus beta 1 into u, and the third state variable is, let's suppose, x3, that is defined as the derivative of the second state variable x2 minus beta 2 into u. So these are our three state variables. Why there are three state variables? Because the order of this equation is 3, first of all, and secondly we will be using three integrators to relate the y triple dot with the y. Okay, so the number of state variables are equal to the number of integrators used in the differential equation. So there are three state variables over here, x1, x2 and x3. Now starting with the definition of the first state variable, that is x1, we have considered it equal to y minus beta naught into u. So I can write down that my output, that is y, that will be equal to x1 plus beta naught into u. So our output equation in the state space representation will be written using this equation. So let's call this is equation 1 and this is equation 2. Now taking the second state variable definition, x2 is equal to x1 dot minus beta 1 u, we can write down this equation like this. So what we have done in this equation, we have basically used the derivative of the x1. So x1 is defined by this equation. So if I take the derivative of this one, so this will become x dot, this will become y dot, and this will become u dot. B naught is constant. So using this x1 dot over here, we can write down this equation like this, right? So this is y dot minus beta naught into u dot, and then taking this term from here, so we can define x2 with the help of this equation. And if I rearrange it for the y, so I can write y dot is equal to x2 plus beta naught into u dot plus beta 1 into u. Now from this equation 3, we can write down this equation, that is x1 dot is equal to x2 plus beta 1 into u. So what is this? This is the first order differential equation based upon our selected state variables, right? So this is one of the output first order equations which will be defining this third order differential equation. Because what we do in the state space, in the state space, an nth order differential equation is represented by the n first order differential equation. So this is the third order equation, so we will represent this third order equation with the 3 first order differential equation. So this is our first differential equation in terms of the state variables. Here you can see the first derivative of the x1, this is the second state variable, and this is the input term. So all of these are related by this first order differential equation. Because how we can write this one, this can be written as dx1 by dt, that is equal to x2 plus beta 1 into u. So this is basically the first order differential equation, right? So now let's take the third state variable equation, that is this one x3. So x3 is defined like that. In this equation we can take x2 from here, right? So if we take the derivative of x2, this will become x2 dot, this will become y double dot, and this will become u double dot, right? And this will become u dot. Beta 0 and the beta 1, these are the constants. So if we take the derivative and replace it over here, so this term comes from equation 4, right? And minus beta 2 into u is from this one. So this equation can be written like this, and if I rearrange it for the output, so y double dot will be equal to x3 plus beta naught u double dot plus beta 1 u dot plus beta 2 into u. And using this equation we can write that x2 derivative is equal to x3 plus beta 2 into u, right? So that is shown over here. So this is our second first order differential equation. Along with this this equation, that will be defining our this third order differential equation with the derivatives of the forcing function. Okay, so we have defined two equations, the first one and the second one. Now using this equation I can write an expression for the derivative of our third state variable, that is x3. So x3 dot will be equal to, we are taking derivative of this one, so this will become x3 dot, this will become y triple dot, this will become u triple dot, u double dot, and the u. These are the constant beta 0, beta 1, and the beta 2. So taking derivative we can write this equation like this. Okay, so in this equation we have only the state variables x1 and x2 in the input. In this equation we have the state variable and the input, but in this equation the third first order equation is required, x3 dot, but on this side, on the right hand side, we have the y triple dot, u triple dot, u double dot, and u dot. So we need to now eliminate these ones. So we can replace this y triple dot in this equation from here, right? So if I use this value of the y triple dot from equation B, so first of all I can write it in the form, I can reduce one order of the derivative. It will be in terms of only double derivative, single derivative of the output. So using equation B, in this equation we will get this equation. Over here what we have done, we have replaced this y triple dot from the equation B, and rest of the terms are over here, right? So this is beta naught into u triple dot minus b1 u double dot minus b2 into u dot from this equation. Okay, now what we are going to do next, we are going to use the expression for y double dot, y dot and y from the equations those we have defined above. And what are those equations? Here you can see the y is defined by this equation, equation 2, y dot is defined by this equation, that is equation 5, and y double dot is defined by this equation, that is equation 9. So using this equation 2, 5 and 9 for the y dot and y double dot, we can write down this equation like this. So this is y double dot, right, and for this y dot we have this one, and for y we have this expression, and rest of the terms are exactly taken from this equation into this equation. Okay, now if I rearrange this equation, I can write it like this. So minus a1 x3, then minus a2 x2, and then minus a3 x1, then collecting the terms of the triple derivative of the forcing function. So where it is present over here, that is minus beta naught into um, triple dot u, and it is also present with the beta b naught, right. So collecting these derivative terms over here, so I can write it like this. Okay, so in this equation one thing that is I think missing, that is this is with triple dot taken from here, b naught triple u triple dot and b naught u triple dot. Okay, so now b naught u triple dot and beta naught u triple dot, so combining them together in one term. Now collecting the terms having the u double dot, so one term is this one with b1, the second term is this one minus beta 1, and the third term is over here minus a1 into beta naught. So these are the terms with u double dot. Now collecting the terms with the u dot, so minus a1 into beta 1 minus a2 into beta naught, then we have beta 2 with b2 with u dot and minus beta 2 with u dot. So collecting all of these terms over here for the u dot, and similarly collecting the terms for the u. So we can write down this equation like this. So now to make the derivative of the forcing function 0, we will have to select beta naught, beta 1 and beta 2 in such a way that this coefficient that is with the u triple dot should be 0, right. So first of all, taking this equation over here and letting it equal to 0, so we can define that beta naught should be equal to b naught. If this is like that, so this term is going to become 0. Similarly, we are going to take this term and we are going to set it equal to 0, as you can see over here, and by rearranging we can say that the beta 1 should be equal to b1 minus a1 into beta naught. So if the beta 1 is equal to this one, this term will become 0. That's the derivative of our forcing function, second derivative of the forcing function. Similarly, by setting this one equal to 0 over here, we can express this beta 2 in terms of these previously defined coefficients or the constants. So b2 minus a1 beta 1 minus a2 beta naught will give us the value of the b2. So with these, what we will have, this will be equal to 0, this will be equal to 0, and this will be equal to 0. All the derivative terms of the forcing function will become 0. So only term that will be left, that is this one, that is the term of the input u, non-derivative term. Okay, so let's suppose that this is equal to beta 3. So b3 minus a1 beta 2 minus a2 beta 1 minus a3 beta 2, that is equal to b3, right. So the betas are defined like that. Beta naught is equal to B naught, beta 1 is equal to B1 minus A1 beta naught, and this is the equation for beta 2, this is the equation for beta 3. So if we generalize it for nth order differential equation, so we can say that the beta n will be equal to, as we look at the trend over here, 0 1 2 3, so this will be represented as bn in the bn beta n, and this is a1, but over here you can see the betas are changing from 0 to n. So this will be a1 into beta n minus 1, then minus a2 starting from beta 0 to beta n minus 2, and so on. So we can represent beta n with the help of this equation for the nth order differential equation. But we were discussing the third order, so we keep our discussion limited to these equations. Okay, now using these values of the betas, what about this equation? This equation C. This is going to become 0, this is 0, this is 0. So we can write this equation C like this. X3 dot, that is equal to minus A1 X3 minus A2 X2 minus A3 X1 plus beta 3 into U. And if I rearrange it, I can write it like this. So this is our third first order differential equation in terms of the state space variables. X3, X1, X2 and X3 are our state space variables, and the U is the input. So this is the first order differential equation, and two first order differential equations we have already defined. Here you can see the X1 is given by this one, right? X2 is given, X2 dot is given by this equation, and X3 dot is now given by this equation. This is the first order differential equation. So these are previously defined ones. So now these three equations, X1 dot, X2 dot and X3 dot, now can be written like this. X1 dot, as you can see from here, this is only the function of X2, so 0 X1 and the 0 X3, but with X2 the coefficient is 1, and with the input we have the beta 1. Similarly, from this equation X2 you can write down this equation, and this X3 rearranged can be written like this. Now from these three equations we can write down the state space equations, state space representation of the system. So this is the matrix of the state variables, the derivative of the state variables x dot. So x, you can say a vector which consists of three components, x1 dot, x2 dot and the x3 dot, which are basically the state variables. And then defining a matrix from this set. So here you can see 0 1 0, and from here 0 0 and 1, and from this part a3 minus a2 and minus a1, and again the matrix of the state variables. And then from these three terms, beta 1, beta 2, beta 3 into input u. So the output equation, as I told you before, is this one. This is equation 2, that output is equal to x1 plus beta naught into u. What is x1? X1 is our first state variable. So using this equation over here, y is equal to x1 plus beta naught u, I can write down that our output y is equal to 1 0 0 into the state variable matrix. So x1, x2 and x3, these are our state variable. So as we want x1 at the output, so that's why you can see 1 over here. This is not there in the output equation, so you can see the zeros over here, right? Plus beta naught into u. So now if I compare it with the standard representation of the state space, that is x dot is equal to ax plus bu and y is equal to cx plus du. So this is our matrix A, the state matrix, and this is our matrix B, that is the input matrix. This is our matrix C, that's the output matrix, and this is our matrix D, that is the direct transmission matrix, that our input U is directly linked with the output through this direct transmission matrix. Okay, so comparing it with the standard set of state space equation, we can now determine the matrix A, B, C and D for this differential equation in which there were the derivatives of the forcing function, right. So what we need to do in order to represent any nth order differential equation in terms of n first order differential equation, we need to calculate beta 1, beta 2 and the beta 3. These are the coefficient from the equation minus a1, minus a2 and minus a1. You can directly get these variables from the equation. Here you can see a0, a1, a2, a3. Okay, one more thing over here, that in this discussion I have assumed that a naught is equal to 1. So in the standard form we will consider a naught equal to 1, right. So a naught is equal to 1. With this a1 is used at this entry, a2 is used over here, a3 is used over here, and the betas are calculated according to the set of equation that we defined over here. Beta naught from here, beta 1 from here, beta 2 and the beta 3 over here, right. So we can represent any system with the help of this set of equation, and nth order differential equation can be represented in terms of n first order differential equation, right. So here you can say that this is our first order differential equation, second first order differential equation and the third first order differential equation. So by defining the state variables, we have set all the forcing function derivatives equal to 0, and we have represented the system with the first order differential equations, right. So for the nth order differential equation, we can generally define the state space representation like that. So nth order differential equation is this one. You can see a1, a0, a1, a2 up to an, and then there are the nth derivatives of the forcing function. So this can be represented with the help of this equation, right. So this is our state space matrix A. So you can see over here 0 1 0 0 and the a ones are moving like that, and these are the coefficients from your output side, output terms, and the beta 1, beta 2 and beta 3 are calculated as we discussed before, and the output is linked with the first state variable x1. But it's not necessary that you are going to put 1 over here. If you want to observe x3, so you can put 1 over here. So by putting it over 0, so what you will be observing at output, you will be observing x3. Similarly, if you want to observe x4, so you can put 1 over there, right. So you can observe any state variable at the output, but generally as we have defined the procedure, for that we are observing x1 in this procedure. Okay, so by comparing it with the standard state space equation, this is the state matrix, this is the input matrix, this is the output matrix, and this is the direct transmission coefficient matrix. So nth order differential equation can be represented in terms of space vector like that, and these betas beta 1, 2 and 3 can be calculated with the help of this equation. So if I conclude, what we have done, we have learned a technique that how we can represent an nth order differential equation in terms of an first order differential equation, and how we can write down the state equations, and how we can determine the matrix A, B, C and D to represent the differential equation in terms of state space equations. In the next video we will see the examples related to the state space variables. Thank you very much.